Now that we know a little bit about how waves combine, we can look at an example of interference known as Young's double slit experiment. So the way we would do this now, if we have monochromatic light, which means light that's all the same color, nowadays we'd use a laser. They had to do something else 150 years ago when this was first done. We run it through a slit, and we'll find out that what that makes it do is spread out in all directions. So then that light, and notice these are wave fronts hitting this second screen that has two slits in it. That light, the light leaves here, each slit is in phase with the other. So the peaks, a peak is leaving S1 at the same time a peak is leaving S2, and we shine it on the screen and we get this pattern of light and dark lines. So the reason we use light of a single color is that it's a single wavelength. So the geometry that we're going to see below is the same for all the light. The width of the slit can't be gigantic compared to the wavelength of light. We know the wavelength of light is very small. It's for visible light, it's hundreds of nanometers. The slit doesn't have to be hundreds of nanometers in size or smaller, but it can't be. This can't be like 20 centimeters, some giant window-sized opening, or we won't see this effect. So we have two sources now that are in phase. They start off completely in phase, and they're sending these wave fronts. You see there's blue solid lines and blue dotted lines to represent the wave fronts from S1 and S2. And if you look at these yellow curves, for example, this yellow curve goes through places where the waves are out of phase exactly. One of them is a maximum, the other is a minimum. We get a dark spot there. On the other hand, if we go through this yellow curve, this is where the light waves are in phase when they reach the screen, and we get a bright spot. So this pattern, this is how we get these bright spot, dark spot, over and over and over again patterns. If we want to look at the point that's at the center between these two exactly, notice that that's a maximum. And the reason is both of these slits are exactly the same distance from our point right here. If they're the same distance and the wave started out with the same phase, they have to both end up here with the same phase. If we go a little bit above that, notice that what that means is the light from S2 has to travel a longer distance than the light from S1. This is how they get out of phase. This one will have to oscillate more. More waves will fit in here than will fit here. They end up out of phase exactly at this point, and we get a dark spot. To see this geometrically, it could be a little bit easier to write it like this. So here we have our two slits that are some distance d apart. Now remember, the slits are not huge on the scale of wavelength of light. This distance d could be several centimeters. That doesn't have to be small compared to the wavelength of light. If we look at some point on the screen, some particular point of interest, we see in this case it's closer to the top slit than the bottom slit. We want to know how much extra distance does this purple path measure compared to the blue path. So the extra part is down here from the green line to the slit. This is distance that the light from the bottom slit has to travel that the light from the top slit doesn't have to travel. So that extra distance is what determines whether they're going to arrive here in phase or not. And we could figure out what that is by doing a little bit of trig. We know that we have a right triangle here. This black line that separates the slits is the hypotenuse. This green line here and the purple line here all give us a right triangle where this is the right angle. And this theta here is the same as this theta, which we get when we move up the plane by a certain amount. So we start here at theta equals 0 if we're interested in this point. We keep moving up, theta is increasing. This theta increases too, since they're the same thing. The extra distance is d, the slit separation, times the sine of theta. So if we look at this, it doesn't matter when we look at these waves, this blue and red that are going to add to green. All that matters is the relative phase. This one's at a peak and this one's at a peak at the same time. It doesn't matter if the blue wave really started way over far to the left and the red wave started right here. So it doesn't matter how many extra cycles are involved. All that matters is the fractional cycle. Do they line up to within a fraction of a wavelength? So if they're off by a whole number of wavelengths, we'll never know. If you want to think about a similar idea, let's say we have two, regular analog clocks, the kinds with hands, and they show the same time. That's all we can ask of them to say that they're keeping the same time. We can't tell if one of them is really 5 years older than the other, so the hands have gone around thousands and thousands more times in one than the other. All we can see is what's their position right now. So we go back to our interference picture. If this path difference between two waves is a whole number of wavelengths, like this, the waves are in phase, we get a bright spot. On the other hand, if the path difference is a half whole number of wavelengths, half odd integer of wavelengths, the waves will be out of phase and we'll get a dark spot. So we want to calculate this extra length in terms of things we can measure. We can measure this angle theta easily enough, and we can measure d easily enough. So what we end up with, we're saying that for constructive interference, we want this extra path difference, d sine theta, to be equal to a whole number of wavelengths. So m is any whole number. Negative 1, 0, 1, 2, 3, any of them are fine. By tradition, we count up here as positive m and down below that as negative m, but it doesn't have any physical significance. On the other hand, if we want destructive interference, we could write it like this. This extra distance, d sine theta, is m plus a half, where m is still a whole number, lambda. So now we know we're out of phase when we get to the screen. So what kind of test or homework question could we ask? We could say we have a laser of this wavelength, 630 nanometers. It's shining on two slits that are 5.2 micrometers apart and 1.9 meters from a screen. What's the distance on the screen from the central maximum to the third minimum? So this would be the central maximum. This would be our third minimum. This is what we said was 5.2 micrometers, that distance d. How do we calculate that? First, we have to find the angle to the third minimum. So we put in d, which is 5,200 nanometers if it's 5.2 micrometers. Sine theta equals 2 plus a half times 630 nanometers. Why 2 when we said the third minimum? Well, the first minimum would be at m equals 0. The second would be m equals 1. The third is m equals 2. So now we solve this with algebra. We get 2.5 times 630 over 5,200 gives us this fraction. We use the calculator to take the inverse sign, and we get 17.6 degrees. Now, if we have that angle, we can draw a right triangle where this is 17.6 degrees. This is the distance between the screens. We just want to know what x is. So what we would do in that case is say, all right, 1.9 times the tangent of that angle, that tells us how far up the screen our m equals 2 third minimum is. So we can locate it that way. And of course, we could change this question to be, the third maximum, the second minimum, the second maximum, whatever. We could change the wavelength of the light. We could change the size of the slit. But other than that, it's all pretty standard. You'll see this question in every physics book.